When people see a complex fluid render like this, they immediately classify the software as a specialized tool for animators and digital artists. That assumption causes mechanical engineers and computer science researchers to overlook one of the most capable open source platforms available today. The visible interface, the viewport, the objects, and the rendering engine is actually a superficial abstraction. Beneath the UI sits a high-performance visual computing environment. It is a space where geometry processing, physical simulation, raw rendering, and programmatic automation execute simultaneously. Traditional creative applications restrict users to a fixed set of drawing tools, while Blender operates as a structured system for managing spatial data. It functions as an open, programmable platform where writing code and generating visual output are inextricably linked. To see how this works, we have to deconstruct its C++ and Python architecture, examine its use of data-driven procedural logic, and look at its role in modern artificial intelligence pipelines. Treating this environment as a mere drawing tool is a failure of systems thinking. Assessing its full utility requires analyzing the platform through the lens of software engineering. Standard design software often relies on monolithic black box architectures. Users can interact with the interface, but they cannot modify or automate the underlying core behavior. This diagram shows Blender's solution, a decoupled layered stack separating computation from interaction. At the foundation is the C++ core engine built for pure performance, handling the massive mathematical lifting for geometry processing, ray tracing, and physics simulation. This core is purposefully abstracted. A developer does not need to write raw C++ to manipulate those physics or alter that geometry. A Python application programming interface or API sits directly on top of the core, acting as the high-level control mechanism. This Python layer drives the user interface, custom tooling, and workflow automation. These two layers communicate rapidly and bidirectionally. The flexible Python sends commands down into the heavy core, and the core instantly returns computed results. This structural split provides a massive engineering advantage. Developers write simple Python scripts to automate vastly complex native C++ operations without ever having to recompile the software. By isolating heavy computation from logic controls, the system operates as an extensible development lab rather than a fixed function application. Inside this architecture, a 3D model is never a static picture. It is a live, accessible data matrix. Every object mesh, material property, camera coordinate, and light path exist strictly as structured data. The core value of visual computing applies here. The moment a shape is represented as structured data, it becomes mathematically programmable. This split screen comparison illustrates the difference. On the left, traditional modeling requires a user to push individual vertices by hand to create a single result. On the right, procedural summation takes an algorithmic approach. Blender handles this spatial programming through geometry nodes, a visual programming language built directly into the software. These nodes act as logical operators, applying math directly to geometry data. Altering a single integer in the logic graph instantly multiplies the initial beam, mathematically weaving it into a complex, parameterized architectural trust system. This workflow relies on core engineering principles, defining rules, abstracting patterns, and building reusable systems instead of executing one-off manual labor. Geometry Nodes teaches algorithmic reasoning and system-level design. It acts as a computational gateway extending far beyond the utility of a standard 3D modeling feature. Because the environment operates natively in Python, it integrates seamlessly with external technologies. This enables applications in machine learning, data science, computer vision, and autonomous robotic research. A primary bottleneck in modern artificial intelligence development is training. Neural networks require massive amount of perfectly labeled visual data to learn, which is slow and expensive to capture in the real world. Blender acts as a synthetic data factory. It generates infinite training environments, rapidly iterating through day and night cycles, weather conditions, and shifting camera angles. This automated data pipeline shows how Python scripts extract specialized machine learning data layers directly from these 3D scenes. The system outputs a grayscale depth map, then applies semantic segmentation, and finally generates precise bounding boxes to track individual elements. Every variable, from lighting intensity to object placement and camera lens distortion, is randomized programmatically to create robust, unbiased datasets. This automated generation forms the foundation of a human-in-the-loop workflow for artificial intelligence. While AI models generate raw visual assets or raw code, this platform provides the structured procedural environment where humans inspect, refine, and physically simulate those outputs. The programmable nature of the software makes it the essential laboratory where AI-generated output is given strict structure, mathematical control, and actual production value. When you aggregate the impact of a heavy C++ core, high-level Python automation, and programmable geometry, the resulting platform operates at an incredibly high level. These combined systems enable advanced engineering outputs. Users generate precise digital twins of manufacturing hardware, create automated exploded views of mechanical assemblies, and procedurally build entire cities from raw GIS data. This technical reality challenges how university engineering and computer science departments currently structure their software curriculums. The traditional method relies on teaching programming, physical simulation, and graphics in completely isolated, siloed software ecosystems. By utilizing Blender, institutions gain a unified, open source computational lab. It offers simultaneous skill development. Students learn Python scripting, data structures, visual computing, and AI pipeline management, all within a single environment. The historical wall that separated technical engineering software from creative media software is now entirely obsolete. The future of technological development demands professionals who can fluidly cross the boundaries between logic, automation, and visual representation. Blender functions as the computational engine required to construct the future.